Hi guys, my name is Sochi Luna and today I'm going to explain a big concept in math and science, vectors. Although they aren't exactly visible, a lot of forces in our world can be defined and explained using vectors. So what is a vector anyways? A vector has both magnitude and direction. Now that we know what vectors are, let's try a real world example. My friend Demi likes to mess with me a lot. She tells me that she's going on a plane and she wants me to meet her at her destination. The trick? The only clues she gives me are her starting point, air velocity, and wind velocity. Demi's plane takes off from LAX, or Los Angeles Airport. The air velocity is 575 miles per hour at 299.6 degrees from north. The wind velocity is 132.1 miles per hour at 13.3 degrees from north. So where in the world is Demi headed? First, let's address what she means by degrees from north. When we're measuring in degrees from north, we'll start at the positive y-axis and move clockwise. For example, 90 degrees from north is the positive x-axis. When we draw out the air vector, it'll look something like this. Now, in order to add our vectors, we want to find the x and y components of each vector. Using the bearing Demi gave us, we can find out that this angle here is equal to 29.6 degrees. If you remember your trigonometric identities, you know that the sine of 29.6 is going to be equal to the opposite side over the hypotenuse, or Vy over 575. Solving for Vy will give us 284 miles per hour. We'll use a similar method to find Vx, velocity in the x direction. Cosine of 29.6 is going to equal Vx, or the adjacent side, over the hypotenuse. So we'll use the cosine function here to find out that Vx is equal to 500 miles per hour. But we might have a little bit of an issue here. Vx seems to be going in the negative direction if you take this to be like the coordinate plane. So we're going to change that to negative 500 miles per hour so we can keep track of where it is that the velocity in the x direction is going. We'll use a very similar method to find the Vx and Vy of the wind velocity vector. Again, because of the bearing Demi gave us, we know that this angle here is 13.3 degrees and that the magnitude of the wind velocity is 132.1 miles per hour. Using sine of 13.3 is equal to opposite, or Vx, over hypotenuse, 132.1, we find that Vx is 30.4, and using cosine to find y yields 129 miles per hour. In order to add our vectors, we'll need to draw them so that the endpoint of the air velocity vector is the same as the starting point of the wind velocity vector. Then our ground velocity vector will start at the starting point of the air velocity vector and end at the ending point of the wind velocity vector. In order to find our ground velocity vector, we'll have to draw in the x and y components of our air and wind velocity vectors that we calculated previously. As you can see, the x component of the ground velocity vector is going to be equal to the x component of the air velocity vector plus the x component of the wind velocity vector, or negative 469.6. We'll add the y values to find this y value for the ground velocity, which is equal to 413. Then we'll plug this into the Pythagorean theorem, where g squared, or the hypotenuse squared, is equal to Vx squared plus Vy squared, or negative 469.6 is Vx and 413 is Vy. For our ground speed, we'll get 625 miles per hour. Now we know how fast the plane is going, but we don't exactly know where it's going. So we're going to set up this trigonometric equation, where sine theta, or this angle over here, is equal to the opposite side, negative 469.6, over the hypotenuse, or ground speed, 625 miles per hour. Using the sine -1 button on our calculator, we'll find that theta equals 41.3 degrees and that our plane is headed 318.7 degrees from north. When we look at a map of California, we see that San Francisco is the city that's about 41.3 degrees away from LA.